Hello everyone, welcome to my presentation on self-supervised learning based next best view planning for 3D plan reconstruction by a robot. My name is Jianchao. This work was done in collaboration with elders Xin, Shai, and Hurt. We are from Wageningen University and Research. Nowadays, robotics are being used more and more in agricultural tasks such as harvesting, plant phenotyping, and monitoring. To solve these tasks using robots, accurate and robust robotic perception is essential. First, the robot collects sufficient and accurate information using its perception system about the target, then passes this information to the manipulator for downstream tasks. However, achieving accurate robotic perception in greenhouse is challenging due to the existence of occlusions. You may see images like this and this. A commonly used method to solve the problem of occlusion is using multiple viewpoints. Then the information that is not available from a single view can be collected. However, most methods using multiple viewpoints are in a passive manner. They either collect data from fixed viewpoints or moving the camera along a predefined path. This method may work well in a certain scenario, but usually lacks robustness for variations, such as for the plants with different size. Alternatively, the next best view method is being used more and more in recent years to solve this problem. Instead of visiting all kinds of viewpoints, the next best view system estimates the information gain for each view and select the viewpoint with the highest information gain as the next camera pose. Classical voxel-based NBV has been commonly used, even in agriculture domain. But this method is computation and memory intensive. It relies on intensive recasting operations, so it is very slow in information gain prediction. Alternatively, learning-based NBV is very efficient in information gain prediction. This method utilizes a deep neural network to directly predict the information gain for all candidates and eliminates the need for recasting. However, this method requires a large amount of ground truth information gain level training data, so this method lacks adaptability to changing environment. For example, you already have a method that can work well for small plants, but after some days the plant grows bigger, it likely fails. To address these problems, we developed self-supervised learning NBV. Plant reconstruction is a forward process based on the current 3D reconstruction. The neural network predicts information gain for the candidate views to select the next camera pose. The camera then moves to this new pose and collect new data to update the reconstruction. Our idea is we can integrate the plant reconstruction process with a network online training mechanism. During plant reconstruction, all produced data can be collected, and at the end of a reconstruction cycle, this data can be used to update the network. In such a way, we build a closed loop. We just let the robot keep running, and the robot automatically collect training data to improve itself. The right figure gives details about the process. I wouldn't explain much. I would like to say is we do use some techniques to improve the online learning efficiency. For example, we integrated weekly supervised learning with the training paradigm to reduce the need of information gain annotations. We proposed a model-free information gain calculation metric. We used experience replay to improve sample efficiency of training data. Detailed explanation can be found from our paper. This page shows a demo for the method in plant reconstruction through online learning. When with 0% training, the method works very bad. The robot is challenging to choose a correct next viewpoint and even stock in a view. When with 50% training, the method improves a lot, can roughly reconstruct the plant, but still the predicted next view is not the best sometimes. When with 100% training, the network can always make a good decision about the next viewpoint. This demo shows the method can improve its accuracy in information gain prediction through self-supervised online learning. We further evaluated the method's adaptability to novel environments through online fine-tuning. First, we pre-trained the model on tomato plants, and it is clear that the performance improved significantly as training progressed. Next, we fine-tuning the model on paper plants. We observed that even without any fine-tuning, the knowledge learned from tomato plants generalized very well to paper plants. And with minimal additional training, the model quickly converged. Finally, when we trained the model back on tomato plants, the performance slightly decreased. This is likely because the previously learned knowledge was partially forgotten when it has been used a long time for a different environment. This table compares the information gain prediction speed between our proposed self-supervised learning NBV and the voxel-based NBV, which relies on recasting for information gain estimation. The results show that our method is over 800 times faster in information gain prediction. Additionally, we compared the required information gain annotations between our self-supervised learning NBV and an offline learning method that relies on strongly supervised annotations. We found that our approach reduced ground truth annotations by 91% because of the use of weakly supervised learning. Finally, we give a conclusion of the work. We proposed a self-supervised learning NBV algorithm that combines weakly supervised learning, a design information gain metric, and robotics. Our method is over 800 times faster in information gain prediction compared to classic voxel-based NBV. Our method reduced ground truth information gain annotations by 91% compared to offline learning. Our method has the capability to adapt to novel plants through online learning. Also, we found the method is feasible in the real world. Finally, I would like to give thanks to my co-authors and my colleagues. If you have any questions, please contact me through this email, and you can find the paper by scanning the QR code.